minus L. Then we are going to have 200 into 20 minus L. Then, if we are to multiply 100 by 25, we are going to have 2,500 minus 100L. And if we are to multiply 200 by 20, we are going to have 4,000 minus 200L. Let's collect the like term. Minus 100L. This is minus. By the time it calls this equality sign, it becomes what? Plus 200L. We are going to have 400. This is plus. By the time it calls this sign, minus 2,000. Can you see that? This is 100L. We move 25 from 4,000. 2,000 from this, that's 2,000. That's 1,500. Our L will now be equal to 1,500 divided by what? 100. 0 cancel 0. Can you see that? Our L is 15 centimeters. And that will be the natural length or unstretched length, or we can call it initial length of the spring. The spiral spring of a spring balance is 25 centimeters long when 5 Newton hangs on it, and 30 centimeters long when the weight is 10 Newton. What is the length of the spring if the weight is 3 Newton? If you look at this question, it's somehow critical. We are given a spiral spring. By the time we put a weight of 5 Newton on the spring, we have the extension of 25 centimeters, which means before we can have the total length of the spring for each of the weights hang on the spring, you're supposed to have the initial length or the original length. We are going to say let the original length be L. Okay? Then let's take it one by one. For the first load, which is 5 Newton, for 5 Newton load, then the extension will be equal to, because we are given the final length for 5 Newton load. For 5 Newton load, we have the total length of 25 centimeters. So for 5 Newton load, the extension will be, call it E1, will be equal to 25 minus L. That's that. For 5 Newton load, we have 25 minus L. For 10 Newton load, or for 10 Newton force, or 10 Newton load, we are having 30 centimeters for the total length. For 10 Newton load, extension will be, call it E2, that is 30 minus L. We are told that what is the length of the spring if the weight is 3 Newton. For 3 Newton load, they say what is going to be the total length. Okay? The extension will be, let me call it E3, x minus L. I will now put it in brackets, where x is the length for 3 Newton load. That is the total length achieved by the time they put 3 Newton load. Let it be represented by what? By x minus the initial length or original length. These are the things we are having now. This is the a good approach to the question. It's okay? From Hooke's law, you still remember that K, okay? That's okay? So let's now see, we are going to have F1, E1, F2, E2, F3, E3. Let's take it one by one. Our F1 will be when we have 5 Newton load. This is 5. And the extensor produce. Our F2 will be when we have 10 Newton load and the extensor produce. Our F3 will be when we have 3 Newton load and the extension produce will now be X minus L. You can get that. What we are going to do is this. Let's try to equate two of them. 5, 25 minus L will equal to 10, 30 minus L. Cross multiply. 5 into 10 into 5 times 30 will give us 150, 5L. Then we are going to have 10 times 25 will give us 250 minus 10L. Let's take the common minus 5L, common factor, plus, this is minus. By the time it calls this equality sign, it becomes plus. Can you see? Then we have 250, this is plus. By the time it calls equality sign, minus 150. This is 5L. What we are having here, that is 100. If you remove 150 from 250, so our L will be equal to 100 divided by 5. L will be equal to 5 here 1, 5 here. So we are having 20 centimeters. What we have just calculated now is the original length or initial length or the unstretched length, which is L. But what we are after, what we want to calculate is not the original length, it's the final length that we can have by the time we hang 3 Newton load, which is X minus L. Before we can get that value now, let's try and equate the second and third. If you now equate the second, and you can equate any of them, it can be this and this, this and this. Any of the two, you will still get the answer. Let's try and equate 10 divided by 30 minus L will be equal to 3 divided by X minus L. You remember that L already has a value, which is 20 centimeters. Put it there. 10 divided by 30 minus 20. 3 divided by X minus 20. Can you see that the value of X is coming out? Okay. This is 10. This is 10. X minus 20. First multiply. 10 into X minus 20. Then we have 3 times 10, which is equal to 30. This is 10x. 10 times 20, that's 200. Then 10x will be equal to 30. This is minus. By the time it calls this equality sign, it becomes plus. 200. Altogether, we are going to have 230. And it's 10. So x will be equal to 230 divided by 10. Okay? And 230 divided by 10, 0 cancel 0. What you are going to have left is 23 centimeters. Question number 5. An elastic string of length 20 centimeters extends to 24 centimeters. Let's look at that. The initial length, which is E0, which is original length, is 20 centimeters. Then final length, EF, it extends to 24 centimeters. What will now be the total everything original? So our extension will now be equal to 20. We are going to what will now be our extension. Our total length for the whole spring. Let's look at the question. A pneumatic spring of length 20 centimeters extends to 24 centimeters when it's supported by a weight of 50 Newton. Find the energy stored in the spring. Okay? So it's going to be final length minus original length, which is going to be 4. That's our extension now. We are given a force. The force we are given here is 50 Newton. So we are told to calculate the work. What is the work done, or the energy stored in the spring? The energy stored in the spring will be equal to half Fe, which is also equal to half Ke squared. Those are the two formulas we have for the energy stored in the spring. You can also use this formula for the potential energy or work done in the spring. In this case, I will make use of this because we are dealing with force. If we are given K, I will use this. If we are given F, I will use this. So the energy will be equal to